G'day, in this video we're going to be starting Module 6, which focuses on electromagnetism. The first thing that we're going to do is review charged particles and how they behave in electric fields. This is content that we focused on in Module 4, and it comes back again to form the basis of Module 6. This video focuses on syllabus content 6.1.1. We're looking at the first dot point in Module 6, electromagnetism. The first inquiry question asks, what happens to stationary and moving charged particles when they interact with an electric or a magnetic field? Again, this is a question that we've already begun to answer in Module 4, but we're going to take a lot further in this video and future videos. This first dot point refers to formula that we're already quite familiar with. So we'll be looking at how we can describe electric fields, charged particles, and how they move within those electric fields, focusing particularly on calculating for electric field, calculating for the acceleration that particles will experience. And that's going to be based on forces experienced, which are applied by the electric field onto the charge. And then we're also going to be looking at work that is done on the charge, incorporating some mechanics concepts in there as well. So our key learning intention today is to revise first electric fields, forces applied to charged particles by electric fields, and then work that is done on those charged particles. So the first slide that I've put together here gives a little bit of a recap of a lot of key concepts that are going to be important to this first inquiry question. First off, I have listed out all of the key variables that are really important to this topic, the corresponding pronumerals and units of measurement, and then a brief description or some additional notes to help you remember what some of those variables are all about. On the right here, we have a bunch of equations which we have encountered before. I've also included these two mechanics equations, our classic Newton's second law and our kinetic energy equation, as they're going to be quite useful to us as we begin to look at the motion of charged particles when they are sitting in those electric fields. Also have some information here from the data sheet which gives us some info on subatomic particles. In particular, you've been told what the charge of an electron is, QE, in coulombs. Something that's really important to note, and I've also written that up here, is that protons have the same magnitude of charge. The size of the positive charge on a proton is the same as the size of the negative charge on the electron. However, the charge is described as positive. We also have some masses here which are going to be important when we start applying our mechanics equations included. I'm not going to talk about each little piece on this slide in detail. I strongly recommend just taking some time to pause the video now, have a quick read of each of these concepts, make sure you understand all of them. If you don't, make sure that you come to class and ask some questions about these specific variables, because you're going to be referring back to them and using them consistently throughout this entire component of the course. As such, you're really going to want to have a good foundational understanding of what these variables are. Something that we didn't spend a lot of time on in Module 4, however, was looking at how you can actually produce or generate an electric field. We focused a lot on point charges and how they behaved. So in other words, objects which were just naturally charged, either because they were a subatomic particle or some other kind of object which was naturally charged. However, in this topic, our main focus is going to be looking at how objects interact in an electric field which has been produced using electricity. What we have here is a pair of charged plates. So what we would do is set up a circuit where there is a potential difference between the two plates. An area of positive charge, which is the plate on the left, and an area of negative charge, which is the plate on the right. The potential difference would be essentially the power supply. And as you move from one plate to the other, the potential of the object would change accordingly. We can see here that in the electric field, we have these uniformly spaced field lines. This is because we assume that an electric field generated by parallel plates such as these are assumed to be uniform. What that means is the electric field is the same at all points, meaning that the electric field will influence a charged object that's inside it uniformly no matter where it's positioned. Now, the size of this electric field is going to depend on the potential difference between the two plates, as well as how far apart the plates actually are. Note too that the field lines always go from positive to negative. That's because they're pointing in the direction that a positive charge would move if it was placed inside the field. If you have a negatively charged object, its force and motion will go in the opposite direction. Let's have a go at applying some of these concepts now. Here we have a scenario where an electron is placed between two charged plates 3 centimeters apart. Let's assume that they're parallel, even though the question doesn't say so. The negative plate has a potential of -5 volts and the positive plate has a potential of 8 volts. What we're being asked to do first is calculate the electric field that exists between the two plates. Now, what's really important when completing a question like this is if you don't have a diagram to begin with, make sure you draw one. If you are given one, there's probably room to make some annotations to extract some of the data out of the question and make it really clear exactly what variables exist and how they relate to the space that exists within the diagram. We'll start by drawing out our parallel plates first. Our first plate on the left will be positive, and our plate on the right will be negative. If that's the case, then our electric field lines are going to be going from positive to negative, left to right. And I'll label that as E for our electric field. From here, what I want to do is then identify any other information that could be found in the question. First off, we know that the positive plate is exactly 8 volts and the negative plate is exactly 5 volts. And that the distance between the two plates is 3 centimeters. Now, the other helpful piece of information that we have is that the potential difference here, delta V, is equal to 13 volts. And that's just simply equal to the difference between the voltages across the two plates. From here, we can start to calculate for part A. And what I'm going to do is use the equation from our data sheet that E is equal to potential difference divided by D, or that E is equal to V on D. Now, subbing that in is pretty simple. The only thing that we have to be wary of is making sure that we convert our distance to meters. So that's going to be 13 divided by 0.030 meters, which gives us, correct to two significant figures, 430 volts per meter. We could also express this in newtons per coulomb. Now, what's important here is to also describe the direction of the electric field, because we haven't really been given any points of reference within the question itself. Rather than giving like an up, down, left, right, north, south, east, west kind of direction, the best way to describe the direction here would be towards the negative plate. And there we go, part A is done. Now, the second part of the question, part B, asks us to calculate the acceleration of the electron when it's in the field. And it actually requires us to combine knowledge and skills that we've learnt throughout our modules in Year 11, particularly from Module 2 and Module 4. There is a way to link together the motion of particles in an electric field and their acceleration, and it's going to be done using these two equations. The first being F equals ma, which is, as we know, Newton's second law. But we also have that F is equal to QE, which was a formula that we learnt about in Module 4. And this talks about the force that is experienced by a charged particle. And that force depends on not only the electric field and the strength of that electric field, but also the charge of the particle itself. What we can do from here is assume that the two force values in these equations are going to be equal. In this case, we're talking about the force that's being placed on this electron. So we can say that the mass of the electron times its acceleration is going to be equal to the charge of the electron multiplied by the electric field. Now, we know 3 of these 4 variables. We know Q and N. These are both given in our data sheet. And we also have just found E, which means that we can rearrange our equation for A. That is that acceleration is equal to QE times electric field on ME. I will very briefly just put in a little bit of a data column to make it really explicit the values that are being substituted in. And from here, we will then substitute. Now the answer that we get is negative 7.6 times 10 to the 13 meters per second square. And this is a little bit of an interesting value for an acceleration because it is negative. Now the reason that it's negative is because acceleration will be opposite to the direction of the electric field. In our diagram that we have here on the left, we see that the electric field points from positive to negative, describing the direction that a positive charge will go. However, we know that electrons are negative in charge, meaning that they will move from the negative plate to the positive one. The direction of this force and resulting acceleration will be parallel to the electric field, but be moving in the opposite direction. We also refer to this as anti-parallel. So to clean up the answer a little bit, I'm going to rewrite this as a positive number and indicate explicitly the direction of the acceleration. Now, the last thing that I want to cover in this video is work done on charged particles when they're in electric fields. First, it's really important to note that we have looked at two different equations which describe work as work is equal to QV and work is equal to QED. Both equations are really similar. There's a time and a place to use both. Originally, we defined work as work being equal to Fs, or the force applied to an object over a set displacement. And we also know that work is given in joules. It's a measurement of energy. So assuming that we know other values assuming we have some other measured values about the electric field and the charged particle, we should be able to also account for the work that's being done on said charged particle. I've included this diagram up here as I thought it did a good job of showing some variables which change as particles move through electric fields. But interestingly, they change in different ways, depending on the charge of the particle and where it's moving. So you'll notice in part A, we have a positively charged particle moving in the direction of the field lines. And for part B, we have a negatively charged particle moving in the opposite direction to the field lines. In the case of part A, we have the particle moving from a higher potential to a lower potential. Therefore, we see that the potential difference is going to be less than zero. There is a decrease in potential in this process. However, if the particle is negative in charge, potential difference will increase as the object moves from an area of lower potential, higher volts, to an area of higher potential, lower volts. Note though that for energy changes, regardless of what direction the particle is moving in or the charge of the particle, the change in energy increases and decreases in the same way. In both circumstances, as the charged particle moves to the plate that it's attracted to, there's a decrease in potential energy, a drop in U. This is kind of the same as how an object behaves when it's raised above your head. You've built up lots of gravitational potential energy in it and you've dropped it. The object's gone to where it wants to go and the gravitational potential energy decreases. As a result, in all examples, in example A, example B, or the example that I'm talking about with gravitational potential energy, when you lose that potential energy, you gain kinetic energy. In all of those circumstances, the particle is gaining kinetic energy by getting moving energy. Given all of these concepts, let's have a look at completing a practice calculation which involves an electron from the previous question. In this scenario, we're told that it has moved 1 centimeter towards the positive plate. What we want to be able to find is first the work done on the electron by the electric field, and then the velocity of the electron after it's actually traveled for 1 centimeter. The first thing I'm going to do is bring over our diagram to give us a little bit more perspective. In this scenario, we have our electron, and it's moved 1 centimeter towards the positive plate. From here, let's write up a data column to bring together all of the relevant information that we might need to complete these calculations. While most of this data has been extracted from the question, the data sheet, or from previous calculations that we've done, the important thing here that I want to acknowledge is that I've written down the values for the initial and final velocities. Final velocity is something that we're going to want to know initial velocity may be required, and considering that the electron started at stationary, we can say that Vi is equal to 0. Now that we have our key data, let's start having a look at some relevant equations. The first thing that I'm going to do is write a statement that we know about work, and that is that work is equal to EQD. Note here, really importantly, I'm not using the equation work is equal to QV here. Even though we know Q, we don't actually know V. Even though we know the potential difference across the entire plate, we do not have the potential difference for the electron moving a centimeter across to the left. So because we do not know this potential difference, it's not suitable to be using this equation here. Rather, it's better to be using the electric field and the distance that we have. Technically, if you do multiply the electric field and the distance together, it will give you the potential difference as the electron moves its 1 centimeter across the electric field. But for simplicity's sake, we're going to use the formula which is a little bit more fleshed out and a little bit more direct. What we also know about work is that it is equal to the change in kinetic energy. And kinetic energy can be really helpful to focus on because we know based on our kinetic energy equation that that is equal to half mv squared. So we might have a look at that in part B a little bit later. So let's have a go at solving for part A now. All we need to do is calculate the work done on the electron by the electric field. So the work that is being done is going to be equal to the magnitude of the electric field times the charge of the electron times the distance that the electron travels. So all we need to do here is substitute and solve. And this gives us 6.9 times 10 to the negative 19 joules. Quite a simple equation. Let's have a look at part B. Now the velocity of the electron is going to be dependent on the amount of energy that the electron has. Now the amount of energy that it has depends on how much energy does it have to begin with and how much kinetic energy does it gain in the process of work being done. Now the work equation doesn't necessarily tell us the amount of kinetic energy that the object has. All it tells us is that there is an increase of 6.9 times 10 to the 19 joules of kinetic energy that this electron has gained. However, again, the amount of kinetic energy the electron has depends on how much, not just that it gained, but also how much it started with. So we know that the change in kinetic energy is going to be equal to the final kinetic energy minus the initial kinetic energy, which can be rewritten as such. As highlighted before, the initial velocity is equal to 0. Therefore, this whole section of the equation can be cancelled out. What we can determine here is that Ki is equal to 0, meaning that the kinetic energy of the electron is simply going to be the kinetic energy at its final stage. And this is all equal to the change in kinetic energy or the work that was done on the electron when it was put in between the plates. Effectively here, all we need to do is rearrange and substitute. This comes out to be 1.2 times 10 to the negative 16 meters per second. And as always, because this is a vector, we should also be giving a direction. The best way to describe this is which plate is the electron moving towards, and that is the positive plate. Thank you very much, everyone. In the next video, we're going to start to look at the motion of charged particles, not just in the simple terms that we've explored today, but we're going to start to look at that motion in 2 dimensions. Hint, that's going to mean that we're going to start using some projectile motion concepts that we learnt about in Module 5. But until then, have a good one.